I'm Noah, co-founder of Emerge Tools. Before that, I was an iOS engineer at Airbnb for about 5 years, and during that time, I got to work a lot on iOS performance and sort of low-level optimizations. So we're going to talk a little bit about some lower-level things today and about how to speed up a common operation in Swift. So let's see if the clicker works and get started. Yes, great. So yeah, Swift should be fast. As probably a lot of you know, it's like one of the first adjectives that Apple uses to describe Swift. Like on swift.org, they talk about how it's fast, it's modern, safe, and a joy to write. It's also in countless WWDC talks. They highlight how fast it is. You know, I took this slide from a talk where they said it's safe, fast, and approachable. So they're always pushing that it's like a fast language. So today we'll look at how fast it really is. And there are a few pros for sure, like it's predictable. It also provides like granular low-level control and like low overhead. So what I mean by that is, you know, some languages, like an interpreted language, might have like some overhead that it will have through every line of code that you write. An unpredictable language might do like garbage collection, something like that you don't know exactly when it's going to happen. Swift doesn't do these things, so that makes it fast. But there are also some cons, like abstractions can hide details about what's really happening. And it can be easy to bloat the code to like accidentally end up with a much larger app binary than you expected, and for that to increase the memory used by your app and result in it being slower. There's a really interesting graph from a WWDC talk, last year's talk, Demystify SwiftUI Performance, where they talked about as your code gets more complex, this expectation of performance goes up. And it's kind of like a vague term. It's not exactly clear what they mean by expectation of performance. But there was this quote from the talk where they said, small issues can get amplified, and code that works well for a prototype might not work as well in production. So basically what that means is like as you're writing more code and your app is getting more complex, you have to worry about performance a little bit more. Things that you maybe weren't expecting will start to go wrong. So just a quick audience poll here, like to see where we really are on this graph. Like, who thinks they can write 10 lines of code without having a performance problem? 10 lines of Swift code. 10 lines. Everyone should have their hands up, right? Hopefully. But like, what about like 50 lines of code? Like, anyone go for 50? There are like a couple people. Yeah, 50 lines. Yeah, like 100 lines of code starts to get a little bit harder, right? And like, you know, most apps are much bigger than that. 1,000 lines of code, 10,000 lines of code. It's going to be hard to not have a performance problem. So maybe we can just end the talk here and say, well, that's the answer, right? Just don't write as much code. That would be nice. Then, you know, on this graph, you end up on the easy side and everything is fast. But unfortunately, or maybe fortunately for us, because it means we can have jobs, you do have to write some amount of code. At least for now, AI hasn't like taken over everything, and you know, we still have to write some code for our apps. So we still have to do something to figure out why all this code ends up being slow. So we'll take out our detective magnifying glass here and like look into what's actually going on in the app. To do that, we'll use this tool called ET-trace. This is something that I made at Emerge that's like an alternative to instruments. If you ever had like issues with instruments kind of like being a little slow or janky, you can give this a try. And it lets you visualize the time spent in function calls using something called a flame chart. So I think a lot of you might have not heard of flame charts before, so I'll go over what this is like. This is an example of a really simple flame chart. Basically, it's a bunch of call stacks showing you like that the main function calls setup, run, and finish in this case. And then setup, run, and finish each call their own functions like bar and foo here, right? And the deepest the call stack ever gets in this example is 4 functions, when main calls run, which calls bar, which then calls foo, right? So this is the idea that time is on the x-axis and is showing you as time progresses through running your app, what functions get called and how long they're being called for. So I did this for a large popular app on the App Store and got something like this. Might not be super easy to see. That's fine, because the point of this is that it doesn't actually give you a lot. Like, it's kind of hard to tell what's really going on. You can't really take anything away other than that it took 1 second for the app to launch. That's how long the x-axis is going here. But we can't really tell why it took 1 second. So that brings us to the next thing that we need to be able to do with flame charts, which is to invert them. So you can take a flame chart like this, and you can flip it completely upside down, and you get one like this. And so what's happening here is you take everything at the bottom, and you move it to the top. So the leaf nodes become like the root in this tree. And you merge things together that have like the same name, the same function. So with this inverted flame chart, you can actually tell that the function foo is what's contributing the most to how long it takes to run your main function, because all of those sort of add up at the top, and you can see like that's the slowest operation here. And of course, like main, that was at the top before, and the inverted one is always at the bottom. So that's a really handy tool to be able to see like what leaf calls in all of your stack traces are actually contributing to performance issues. So we can do that for the App Store app also, and it might still be kind of hard to read, so I'll zoom into the top left corner where we can see over 470 milliseconds was in this function Swift conforms to protocol. And there are a bunch of like different variants of this function, but they all have this common prefix, Swift conforms to protocol. So during this app from the App Store launching, this was on simulator on my MacBook, should have been pretty fast, but 470 milliseconds was all in this Swift conforms to protocol. Not even code that you wrote, this is code coming from the Swift runtime. So we want to look at what is causing this to be so slow, and this is sort of our first clue, Swift conforms to protocol. We're going to start from there and see what we can find out. And the next place we'll look is a Swift 5.4 release notes. It was a few years ago, they said that protocol conformance checks at runtime are significantly faster. And they talked about using a faster hash table implementation for caching previous lookup results. So this seems like promising, like it sounds like they're making something faster that is sort of causing the problem for us. But to really understand it, we have to know what a conformance check, what the release notes are talking about here, actually is. And hopefully everyone is familiar with declaring a conformance. It's just like this. You define a type and you say it conforms to some protocol. And then when you do a conformance check, you just take that type and you cast it to a protocol. So it's the as keyword. That's what a conformance check is. But a really important idea here is that this is a runtime operation. And it's similar to a function call. So the as keyword is just like Swift syntax for basically doing a function call into the runtime. And this is very different than what you might be familiar with in other languages like Objective-C, where a cast is not actually going to change how your code runs. It's just going to change how the compiler treats your code. That's not the case here. This is just like any other function call that you're making. Something is happening when you use this as keyword. And what it's doing is something that is a little bit slow. So just taking a step back and looking at where we've got so far, we found out why it's slow, or we found out what is slow, the protocol conformance checks. But we haven't figured out like, why these things are so slow. And we don't know how we're going to make them faster yet. That's where we'll go next. So in terms of why it's slow, the next thing that we'll look at, our second clue, will be this PR to the open source Swift runtime, where they said, re-implement protocol conformance cache with a hash table. That was the title of this PR. And so essentially, it's using a more efficient data structure to do this cache operation. And this is what sped up Swift 5.4. What we saw in the release notes before was this PR. And what they claim from the comment that automatically posted on this pull request running their tests to see how much faster it got was that it sped it up 13 times, so a lot faster, right? Yet we still saw it being slow in our test on the app from the App Store on the simulator. And the key reason that is this is still a cache. And caches have cache hits and cache misses. So the cache hit got a lot faster with this PR where they used a faster data structure. But a cache miss can still be really slow, and that's what's still causing our problem. So let's test this out and make sure we're onto the right track. So I made a test app with 50,000 protocol conformances. I just code-genned that, just wrote a script that spit out a bunch of lines of Swift code that was just class conforming to a protocol. And then on app launch, I checked 50 times if a class conforms to a protocol, and then I did that like 50 times check 3 times. So in total, 150 protocol conformance checks, which was just basically this line like 150 times in a loop, right? The first time I did this, it took 71 milliseconds, the first of those 3 times. That's not great. And then the second and third time, it was very fast, like less than 1/10 of a millisecond. So that's the cache at work. But unfortunately, that first case that took 71 milliseconds, that's way too slow. And we don't want our users to feel like Gloria here. We need something that doesn't take like what should be multiple frame draws during that time just on protocol conformance checks. If you were doing that, if you were using protocols like while you're scrolling, you're going to be dropping so many frames, it's going to be a very janky app experience. We don't want to do that. So the next thing we can test is we can look at using fewer conformances. So I used that like 50,000 one. We can try 10,000 protocol conformances in our app and just see how this cache is sort of behaving. I did the same thing where I ran it 50 times. I checked if a class conforms to a protocol, the same line of code as before, essentially. And this time, it only took 15 milliseconds. So it's like less than a quarter of the 71 milliseconds that it took before. Still a little long. You still don't want like something that seems like it would be so simple to take 15 milliseconds, but it got a lot faster by reducing the number of conformances in the app. And this is a really critical point that is like definitely a way that Swift is doing something unexpected here. At least it was very unexpected for me, that code that isn't running at all is affecting your code. So it violates a lot of what people would usually think about like module dependencies. So say you have an app like this, where you have your login feature and someone else has a payment feature, right? You would expect that any code someone writes in this other module that you don't depend on, but your app still imports, you would expect they could do whatever they want. And like, they could write some bad code and your login feature that has great code wouldn't be affected, right? But it turns out if you put like 1,000 conformances into the other module, that even though you're not depending on it, your code gets slower. That's basically what we're seeing here, is that code that you're not writing, that you're not even depending on anywhere in your like module structure, is actually affecting your code. And I think people have talked about it today, and we'll hear more talks about like refactoring code bases into having modules and like a nice dependency graph. And usually you'd think that that works really well, but this is like a case where it doesn't. And even though you're not depending on the code, it's still slowing you down. So that's kind of this idea of complexity is making it a lot harder to figure out your app's performance and making you need to worry about things that you might not expect. Basically, unrelated areas of apps are getting more complex, and it's affecting your part of the app. And this brings us back to like that first key difficulty with Swift performance, is that the abstractions can hide details. What's basically happening is this as keyword is abstracting away a function call that you might not even realize was happening there, and that function call is seemingly doing a lot under the hood and depending on stuff that you wouldn't expect it to. And that leads to this behavior that's kind of unpredictable. It might be more like unexpected than unpredictable, because really you can predict it if you know what's going on, but it's still confusing. There's a cached state, there's an uncached state, there's code that you don't depend on affecting your code. So you definitely have to really figure out what's going on to be able to predict it. So in order to get better at that, we'll look at what actually is going on, like from the compiler point of view when you add a conformance to your app. So not just the source code that we saw before. What ends up happening is the compiler puts a list of all the conformances in your app into this section in the binary called Swift5 proto. And each entry in this section is a type protocol pair. So the type that is conforming to the protocol and the protocol that it's being conformed to. The layout of this is defined by the Swift compiler, and it's part of the ABI, the application binary interface. So that means like it probably won't change, or if it changes, it needs to change in like a compatible way, so that if you build an app with like an old version of Swift and run it on a newer version, everything still needs to work. And it looks basically like this. There are like these 4 fields in a protocol conformance descriptor that gets emitted into your binary. One of them is a pointer to the type, one is a pointer to the protocol, and the other 2 are just sort of like flags, and the witness table is to look up the functions that your protocol requires you to implement. But this is what ends up happening. So if you have 50,000 protocol conformances in your binary, you'll have 50,000, or in your source code, you'll have 50,000 of these structs in your binary. And at this point, you might be thinking, why does any of this matter? And explain it in like a much easier to understand way, because you don't work on the compiler, right? But I think it actually does matter for a simple reason, is that you can build cool things with it. So this is actually like how I got started with my company at Emerge. Like when I first started the company, the first thing I built was this size analysis tool that lets you visualize the size of your app binary. And it worked by parsing the metadata in the Swift binary. So that's where I first learned about these things. I was looking up in the Swift compiler and other people's blog posts about how the binary is laid out, so that I could figure out like how much size can be attributed to different types, like the protocol or the type that's implementing the protocol. So that's one thing that you can do with this, is you can understand why the binary is a certain size and what's causing it to generate that code in the binary. But another cool thing that you can build with this is a function like this. Like typically, I think that this would be pretty difficult to implement, like a function where what you want it to do is return all the types in your app that conform to preview provider. And you might want to do something like that with like code gen, or you could manually list, like if you have 100 previews in your app, you could type 100 lines of code here and have it return all of them. But I wanted to be able to do this dynamically, where my code essentially wouldn't even have to depend on everything else in the app. It could be like its own module. And that's similar to like Objective-C copy class list, if you worked with that before, like something that the runtime will give you a list of all the classes in your app. But trying to do this for Swift wasn't exactly clear how this could work. But it turns out this exact same thing we've been talking about, protocol conformances, if you know that they're there in the binary, you can scan them all and return them from this list. And that's how I built this snapshot testing product that my company also has, that it basically looks like this. Like it can find all the previews in the binary and just render them on the screen and save them to an image. And this is all open sourced also, so if you're interested in like how to use this knowledge about how protocols are laid out in the binary. You can take a look at the source code there and see it's opening that binary section that I talked about, the Swift5 proto section, iterating over every pointer in it and finding the types that it's basically chasing these pointers around the binary until you find the type that conforms to it. So some interesting things that you can build by knowing how these things work. But getting back to the main idea of why is this slow? So if you look at that PR that I talked about earlier that implemented the faster cache, you see that it all is happening in this function Swift conforms to protocol maybe instantiates superclasses. And there are sort of three high-level paths through that function. The first path calls find conformance with DYLD. We'll return to that one in a few minutes. The second one is to search in the conformance cache. That's exactly the cache we've been talking about, the one that got 13 times faster with Swift 5.4. But then the third path is a linear scan of conformances. And this is our third and final clue in figuring out what's going on here, is like a linear scan. It should be like a red flag. It's not something that you want to do for performance. And it basically means that it's going to be an O of n operation. So it means that as your app gets bigger, this is getting slower. If your app gets twice as big because you have twice as many conformances, it'll get twice as slow. But I'm actually claiming that this isn't just O of n. What's really happening here is something that's O of n squared, which is much, much worse. And the reason is that it happens every time a conformance is checked. So it's not just like one time you're going to scan everything in the binary where you're conforming to a protocol. It's every time you use the as keyword. So if you say like X% of conformances in your app are used, like maybe 40% of your code ends up actually getting used, you could end up writing like some pseudocode like this to get an idea of what's happening. Basically, from all the types in your binary, some 40% of them are getting used, and then you're looping through all of those. But within that loop, you're doing another loop. That's the n squared operation. So you have this outer loop and this inner loop. And it's kind of like the analogy that I like to think about is like if you were trying to order off a menu at a restaurant and you needed to order like 40% of the menu. Maybe you have a really big group. Maybe you're ordering food for a conference, right? A lot of people. And you basically, every time you order a new item, you have to read the whole menu. That'd be really slow, right? You only would want to read it once. But that's kind of what's going on here. Is like every time you look at a new item, you have to read through all of the items. So we don't want that. That's going to make something very slow. And one thing that we can actually do is we can increase the unused percentage by removing the things that aren't used. So ideally, you wouldn't have like 40% of your protocol conformances actually checked. You'd have 100% of them. And so you could make the inner loop smaller by removing all the unused ones. And there are various ways you can do this. Like there are lots of dead code detection tools. Like Periphery is one people might be familiar with that statically analyzes your code and finds things that you can delete. I also make one at Emerge called Reaper that is complementary to Periphery. It runs in production and helps you find code that the compiler thinks is used, but in reality maybe feature flags make it never hit. And the more of these you can remove, the faster these operations become. But they are still going to be O of n squared. That's the key takeaway, and the answer to why it's so slow is that this operation is an n squared. So if you add twice as many protocol conformances in your app, you'd expect your app to be 4 times slower. If you add 4 times as many, like 16 times slower, right? It really adds up fast, makes it a lot slower. So last thing we'll talk about is how we can fix this. It's not all hopeless. Like you can use protocol conformances without it being super slow. And so first, we need to analyze, like, is this really a problem worth even digging into? It only really matters if that n is large, right? But it turns out, like large apps, like the one that I was showing earlier, large apps can have hundreds of thousands of these. So if you work on an app with a big team, tens of people contributing to your code base, it's really easy for this to become larger than you'd expect. A tip to avoid accidentally having 100,000 of these in your app is avoid code genning protocol conformances. Basically, don't do what I did to make this demo, where I code gen 50,000 conformances. And also, one that I see a lot is you can use Codable, right? And Codable gives you decodable and encodable. So if you're conforming your data layer to Codable, but you really only need to decode, like decoding JSON from the network, but you never need to encode it back to JSON, just conform to decodable, and then you're at half as many conformances already. So that will make your app a little bit faster. So the other thing is that these conformance checks, they happen a lot. Even if you don't use the as keyword in your code, you're going to encounter these cases where your app is going through this slow path of scanning all conformances. Code like this, where you just have a generic type, and even if you just reference like .self, like you're not even initializing it, not calling any functions on it, this will still internally cause a Swift runtime to do some conformance checks, even though you're not using the as keyword. Also, if you do like string interpolation like this, internally what will happen is there'll be some protocol conformance checks to see if your type conforms to like custom string convertible, different protocols that you can use to change the behavior of what gets printed in this case. That's all doing protocol conformance checks, so you end up with a bunch of them. The sort of base case for string interpolation is to use mirror. And if you're using mirror directly also, that will internally use more protocol conformance checks. So these, like, even if you are not seeing the as keyword in your code base a lot, it might still be happening. It probably is. So it's definitely a problem. What can we do? Well, it turns out iOS 16 did a lot for us. So a couple of years ago, in the release notes, they said apps like Lyft or Airbnb launch almost twice as fast, thanks to improvements in the dynamic linker. And that was all protocol conformance checks getting faster. And what was happening here was this first case, the first path through this Swift conforms to protocol function in the runtime is this find conformance with DYLD. That's using another cache. Like we saw one cache that was in the Swift runtime, but there's another one in DYLD. If you're not familiar with DYLD, it's the dynamic linker. It's what starts your app. So when the first time you tap the app on your home screen, the code that runs is not your app's code. It's the code in DYLD, which is a framework that your app imports that's provided by the operating system. And it is responsible for eventually calling your app's main function and handing over control to your app. But internally, DYLD can do a conformance cache. That's what was added in iOS 16. They added this cache. And it's pre-computed on the app's first launch, which enables like future lookups to be cached lookups that are constant time. So similar to what we saw when we tested it out and we called this thing twice, once this cache is filled, everything will be very fast afterwards, and that's because it's using a hash table. So if you ever practice for a programming interview, a lot of times the answer is hash table. That was Apple's answer here also. Add this hash table in DYLD. It worked very well. This linear scan is just done one time, and it's still an O of n operation, much better than an n squared operation. And it happens before your code even runs, before the main function in your code is called. And then that cache gets saved to disk. And for future app launches, it can reference that and just immediately make all these protocol conformance checks much faster. Those optimizations are also, they're open source in DYLD. And this file called optimizerswift.cpp, it's all in C++. You can find it at this link if you're interested. But the important bit here is like the comment at the top of this file says exactly what I've been saying. It says, the shared cache Swift optimizations are designed to speed up protocol conformance lookups. The optimization builds a number of hash tables to speed up these lookups, saving time and memory. So great, you'd think like iOS 16, that's been out for like 2 years now, maybe I don't have to worry about this anymore. Yet the demo that we saw earlier showed that this still took 470 milliseconds. So there is still something that we need to be doing here. It turns out in DYLD, they're computing this cache on the first launch, but then they're not actually using it on the first launch. So the first time you open the app, there's this ON linear scan being done, the cache is being built up, but then every future conformance check during that launch of the app is still taking the n squared slow path. And each update also causes a new first launch. So if your users are updating your app once a week, that changes the binary, this cache has to be invalidated, and the next time you launch the app, it goes through the slow path again. The cache is also just often disabled even when you're talking about like subsequent launches, like when you're unit testing an app in Xcode, anytime it's running on the simulator, or if you press like the play button in Xcode to run even on your phone, that'll disable this optimization. So that's what was happening earlier when I was testing this on the simulator, is it just isn't enabled on the simulator. But even for users on their first launch of the app, they'll hit this slow state. Also, DYLD is like for Apple platforms, and we've seen already today that Swift can work in other cases, not just on Apple platforms, and server-side Swift is a growing thing, and in those cases there's no DYLD, so this might still be a problem. So what can we do about this? Well, I made something called zconform, which is a drop-in replacement for the Swift runtime that just immediately speeds this up. The way it basically works is normally your app will call functions in the Swift runtime, and this just sort of redirects some of those over to the zconform library. And in zconform, it does exactly what DYLD is doing. It builds a cache of conformances on app launch, but then it actually uses them even on that first app launch. So there's not, it doesn't get disabled like this. This is not meant for production. Like you can't just go and put this in your app and ship it to users, but it can be used for things like in unit tests as a CI optimization so that your tests run faster. And it's a nice POC for anyone who works on DYLD who might be watching to implement things faster there. And you can find it on my GitHub also. And we use it at Emerge also for the snapshot test that I mentioned earlier, because when you do that, you're repeatedly launching the app. And each launch can have this O(n squared operation because the cache is disabled for a variety of reasons. We set some MyVars. We often run it on the simulator that'll disable this. But we want these tests to be very fast because people are running these snapshot tests like on every PR. Our goal is to be not the slowest check on your PR. So other things are what you're waiting for, not the checks that I'm posting, right? So to solve this problem and make them a little bit faster, we just add zconform to immediately remove that overhead and make these run a lot faster. So that's great, but still doesn't help like your actual users. So I want to talk a little bit about things that you can do. I already mentioned deleting protocol conformances that aren't used at all, but you can also think about kind of unnecessary ones. Like if you have a protocol and only one thing conforms to it, you don't really need that protocol, right? You can just use the name of the thing that is conforming to it everywhere that you're using the protocol. Usually this is like maybe something like dependency injection or like mocks for unit tests. You might have a protocol defined that's never used in production but only used in unit tests. So it's good to try to take those out of the production app if you can, like use debug, preprocessor checks to like avoid compiling that in the release version of your app. And that can help make these things a little bit faster. Another really common one that I see is if you use string describing to like identify a type, also can be used for dependency injection sometimes. You can switch that to object identifier, which will give you like a unique identifier for your type rather than the string name of it. And there are no conformance checks with object identifier, but there are a bunch with string describing. So this can, like, if you're doing this a lot in your app launch, for example, this can make things a lot faster. Another one is to prefer using generic functions over like casting things and doing these protocol conformance checks. So an example would be like, say you're logging an event like this, like you might have some analytics functions that takes an event and checks if your event conforms to a protocol that provides the severity of the event. This is doing an extra protocol conformance check, it's that as operation. You can switch that code over to this and define two functions using generics, and then the compiler, as long as the compiler knows that at the call site your event conforms to this protocol, it will call the function that is most conforming this type that's being passed, and give you the exact same behavior, but with no protocol conformance checks. So you can use things like that and really speed these things up by just getting rid of this n squared operation entirely. So just to summarize like where we're at so far, we figured out what's slow, we figured out why it's so slow, this n squared operation, and we see ways to make it faster. iOS 16 did a lot for us, and there are things like zconform that can demonstrate how it can be faster and used in non-production. But in production, you can really look for these in your code and try to optimize it to just not hit this slow path at all. But there's still some ongoing conversation in the Swift community about how to even improve this even more. So just earlier this year, an engineer from Uber started a thread on the Swift forums about this exact issue, protocol conformances. And what they said in the post is that the cadence of our updates mean that the majority of users will have a poor experience once a week. That's because most users will be updating the app once a week, and the first time they update the app, the DYLD cache is not used, and a new cache is built, and during that first app launch, the cache doesn't get used yet, and they hit the slow case through the app, right, where this n squared operation is happening. So they also said that many engineering teams might be wasting time trying to understand this, because it is very difficult to figure out exactly what's going on. There are like multiple levels of caches. Sometimes they're disabled, sometimes they aren't. If you're testing this locally, you might think that the app is super slow, the app that you're working on, because you're hitting this case all the time. But in reality, it only happens on the first app launch. So maybe this isn't like the #1 thing that you should do if even on your second app launch, there are other things that are still slow, right? So it can be confusing to try to figure out like how this should even be prioritized and how much of a problem it is, because in different cases it's happening when you don't expect it. So the proposal in this Swift forums post was to build a faster lookup directly into Swift to avoid the linear scan entirely, to make it so that there isn't this option of linearly scanning all the conformances. But I actually think like a key theme of the talk is like write less code. So try to make this simpler. Maybe we don't want this, because the linear scan is going to have to be there because for ABI stability, right? Like if you built a version of your app with an old Swift compiler and you still want it to run on a new Swift runtime, so the Swift runtime will still have to support this case where the app binary has this structure that needs to be scanned linearly. So I think like a simpler solution might be possible. And One could be just make the DYLD cache a little bit better. Like, it almost works perfectly. If it just worked on the first launch too, there would be no need for this talk at all, because at least real users would never have this problem. You'd only maybe see it in development sometimes, like on the simulator, which can be confusing, but at least not causing performance issues in production. So I think that would probably be the best way to solve this for iOS, at least, is to fix this, update this in DYLD so that it's used all the time. But of course, there could still be issues with non-Apple platforms, because like I talked about earlier, server-side Swift, things like that, where DYLD is not being used to launch the app, there still needs to be something that avoids this like longer lookup in the Swift runtime. So maybe there are other solutions there, like perhaps this mechanism in Swift that's used for DYLD could be made more generic so other platforms could sort of hook the runtime in this way and provide a faster implementation. That could be one way to do it. But it's an ongoing conversation, and if you're interested, you can check out the forum, Swift forums post about it to see what their thoughts are. But sort of in conclusion, what the key things to take away are complexity can cause an app to be slower than you'd expect. So try to reduce the complexity in your app, and once you get it to as little complexity as you can, profile it and try to figure out where these bottlenecks in performance actually are. And sometimes in order to do that, you'll have to dive into these low-level details and see how things are implemented in the runtime, understand that DYLD is there. Performance often involves like looking past these abstractions to see what's actually going on. And reduce the usage of these as operations in your code base and just the amount of times that you're using protocol conformances and conforming things to protocols, because that will just speed up your app entirely. And if you're interested to hear more about this, you can get in touch with me, Sanu3 on formerly Twitter. You can also scan the QR code, or find me after the conference, and I'd be happy to talk more about this or anything else related to Swift performance. There's also a bunch of detail about this on my blog. If you're interested, like a lot of the slides came from things that I've talked about in the blog post, so I go into more depth there. Yeah, thanks.